Camera running.
Okay.
So what are we talking about?
Relativity, apparently.
Einstein's relativity.
There's no other. Alright. Relativity. Basic rule of relativity is that no reference point in the universe is special, which means, like, a lot of people seem to think, for example, that space is like the ultimate reference point. Like, if you're moving to the right and space is not moving, then therefore you're moving to the right, and that's an absolute truth, and there's nothing that can disprove that. When in fact, that's wrong. So, like, for example, if you're in your car and you have like a road here, here's your car. Oh, I don't know. There you go. Look, nice car. And you're moving to the right. You know you're moving to the right, but in all actuality, it is just as valid a claim. Here, let me draw that. It is just as valid a claim to say that your car is sitting still. Hold on, drawing a nice car. And it's just as valid to claim that the world is actually moving that way. So, you know, you're moving that way, everything's relative to you moving backwards that way. That's what relativity states. That's like the number one basic principle. And basically what that means, that implies like a lot of strange things, right? So for example, from every given reference point you measure, light will always measure the same speed. So like for example, if I have my spaceship here, let's go. I don't know. Yeah, there you go. That's a spaceship. No artist. And you're going this way at 1/2 the speed of light. And you shoot a beam of light from a laser pointer here in this direction. This is light. Put a little L. People think that from this reference point, you will actually measure this light as coming out at 1/2 the speed of light, which is wrong, because from your reference point inside the spaceship, and you're looking out the window and measuring the light, from your reference point, the rest of the universe is moving around you, right? So you're not moving this way, the rest of the universe is moving this way, and the light is being emitted. And as we know, if you get on a bike and you start pedaling in one direction, and then you turn on your front light, it won't add the speed of the bike. The light is completely separate from that. So basically, as you're measuring it from this reference point, the light still travels at a constant speed. Right. And this can be held true for everything. If you go in the opposite direction of the light, so if the light were going this way, you would still measure it at the speed of light. From everybody else's reference point, everybody on the outside would logically think that you were measuring it as 1.5 times the speed of light or half the speed of light, but no, that's not the case. And that's just like the basics of relativity. That's special relativity, by the way. There's two versions. There's special in general. So the other half of it is like is the whole wonky time dilation, which is like, so if you have this little racetrack here. I'm gonna rip this explanation directly out of a book because I can't think of a better one. It's really good. And if you're driving down this road, and this is you, and you go from here to here, and let's just say this is a 10-mile road, and you're traveling at 100 miles per hour, mph. It should take you 6 minutes to get from this end to this end, logically. And if you keep running this path, it'll take you 6 minutes every single time, regardless. Now, the thing is if I start to go sort of a little bit askew, it may take me like 6.5 minutes. If I start to go maybe a little more askew, maybe 7 minutes, etc., etc. And that's because you're now sharing your speed between two dimensions. Because you're normally traveling along, this is the y-axis. You're normally traveling along the y-axis, just a straight shot up, right? But now when you start to incorporate the x-axis, and then you kind of start sharing some of your speed through that, now some of the energy is kind of, the speed is diffusing between two dimensions. So now less of the speed is being put in this dimension and a little bit over here, so you're sharing it. So what Einstein said is, if we think of time as its own dimension, right, and here we'll go t, time as its own dimension, and you have a fixed speed through time, as you start to travel through space, normally you're just traveling directly through time, but if you start to put some of that towards space, now some of that speed that was set towards time is now put through space. So when you're traveling through space, some of that is moved away from time. So you actually you're aging slower. Your particles are moving through time at a slower rate. Not from your reference point though, because as we stated before, no reference point is special, which means that, so from my reference point, if I'm in something going at half the speed of light, by the way, if you actually add up your speeds through time and space, it comes out to 186,262.2 miles per second, or the speed of light. So if you're going at half the speed of light, you're going through time at half the speed.
Okay.
But, as we stated before, no reference point is special, which means that from your reference point, you're aging at the normal rate. And everything around you is aging at half the normal rate. So that's how time dilation works. It works because you're diffusing your speed from time into space.
All right.
And this is
We
true. We've measured this. We can
kind of wrap it up because
Well,
we're already at 7 minutes.
Yeah, I mean, we can go into general relativity another time, but basically.
So what relativity was this?
This is special relativity.
Special.
This is the first proposed idea, and later he worked with general relativity, which incorporates gravity and acceleration.
Now, he didn't get a Nobel Prize for relativity.
He did not get a Nobel Prize for relativity, but you'll be happy to know that he did get a Nobel Prize for discovering the photoelectric effect.
We'll have to do that some other time.
Well, we did, but it's much easier to grasp on a board.
Okay, we'll
But,
do it another time.
Yeah, so
we'll call it here. So
Yeah,
this
special
is
relativity.
what is it again?
Special relativity.
Special relativity. All right, thanks.
Mm-hmm.